everyone, welcome to this third lesson from the Forces in Space scheme. This one is called Space and Astrophysics, and really it's an introduction to cosmology, and it's one of those rare occasions in school science where we actually bring students in some 20th century science, but obviously we're not really going at this from a kind of a genuinely cosmological perspective where we bring in Einstein's general relativity and so on. We're just the aim of this lesson is just really to give students a kind of sketch of our picture of the universe, and I think what's important here is that they get a sense of scale. The fact that what we used to think of in the time of Copernicus as the whole universe is actually just the tiniest fraction of it. And if they can get that sense of scale from your lesson, then I think they've learned something really profound and really exciting. And that's also useful just as they, as they reflect on their place in the universe. So I'm going to start, when I explain this to students, with the familiar picture, this kind of Copernican model, what we've been calling the solar system. So I'll put the sun in the center, and I'll put the Earth here, like this, and then I can show them, well, you've got Mercury, Venus, maybe let's do Mars over here, Jupiter down here. That's a big one, isn't it? We can put Saturn a bit further out like this. We can do Uranus and Neptune, but I think hopefully they'll get the idea by this point. And what you want to show here is that this is the solar system, as we've been talking about. And in the time of kind of Aristotle and Copernicus, this was kind of thought to be the kind of extent of the universe, in a sense. We didn't really have a sense of how large it was, because at that time it was felt that all of the other stuff was kind of just static, and it was just kind of almost like a painted backdrop, and these were the only bits that moved. But it was only when we developed better telescopes and kind of Galileo and afterwards that we realized there was a little bit more to it. And what I would do here to show students, and remember this lesson is really about scale, it's really about them getting a sense of how everything fits together. I would show that actually what you are talking about here is just a very tiny part of a larger structure. So what I'm going to do here is draw the sun as a star. And I'm going to say that sun is a star here. You could give them this definition, that will be useful later. So a star is something that generates its own energy, it's its own energy source. We don't need to go into nuclear fusion and all that stuff. And planets are things that orbit around stars. And what they need to know is that, yes, this is a star, but this is just one of many stars. So I'll draw one quite close for reasons that we'll see why. But there's lots and lots of stars. All together in this one kind of structure. So I'll draw lots and lots of stars like this. And what you want to show here is that this collection of stars here is called a galaxy. So we think of this as the whole system, but actually this is just a tiny part of a much larger system. And to emphasize the size of that larger system, you might want to give them the figure here. The number of stars in our galaxy, and we'll come back to the galaxy is only a small part of an even bigger system, but the number of stars in our galaxy is about 250 billion. That's the number of stars just in one galaxy. And that's roughly equivalent to the number of grains of sand on Earth. So we're talking a lot of stars. And this is just an amazing fact that they will be kind of super excited to go away with. One thing you can do while you're here, this is a slight add-on in a sense. It's just one of those things that comes up, and this is a good place to do it. Our nearest star is called Proxima Centauri. Don't know if I've pronounced that correctly. I think Proxima Centauri probably just means close star, or next star. It's worth saying that that's 4 light years away. 4 light years. And it's worth just giving students the definition. A light year is just the distance light travels in a year. And that's kind of mind-blowing. That's the closest star to us. And this is kind of a cool idea as well. So that's how far light can travel in 1 year, that's how far light can travel in another year, that's how far light can travel in another year, that's how far light can travel in another year. The point you want to make to students is, with the nearest star that's in our galaxy, what you're seeing, if you see that star in the night sky, is what that looked like 4 years ago. Think about the more distant stars that you're seeing. Actually, you're seeing ancient history there. What they're doing now, we are not going to find out about for another 10, 50, 100, 1,000 years. And students will find this idea mind-blowing, that actually what's up in the night sky is ancient history. And then what's even more mind-blowing is when we say, well, okay, this is the solar system, but actually this is just one star in a galaxy. A galaxy is just a collection of many, many, many stars, billions of stars. But the galaxy is just one structure in an even broader structure, which is called the universe. Now it's worth saying, I haven't mentioned it so far, our galaxy is called the Milky Way. I'm going to label this as the Milky Way. Our galaxy is just one of many, many, many galaxies. So I can draw these. I'm just going to draw these as circles. These are clusters of billions of stars, all kind of joined together, as they'll find out later, joined together because of gravity. They're all kind of pulled together. And there are about 100 million galaxies that make up the universe. So when we talk about the universe, hopefully this diagram, by kind of, usually I tend to zoom in, but actually we're zooming out here. But hopefully they'll see that this diagram, I'm going to draw a ring around that. That whole thing, all of the galaxies in the universe, all of the galaxies collected together, that's what we call the universe. And that's everything that exists. And it's kind of, hard to get your head around. Really, it's an assumption as well, because we call it a universe. Uni means single. We assume there's some sort of unity, all of the matter that exists. But is it possible that there are other universes? These are the questions sci-fi movies like to address, and I'm sure you'll get lots of questions during this lesson. Now, the final thing that you could talk about here, and I think this is really, really important, is to talk about the work that was done in the 20th century by someone called Hubble, and others as well, of course. But what Hubble discovered was that actually, when you measure, what you can do is measure the distance of stars via various methods, and we're talking hundreds, thousands, millions of light years away. When you measure the distance, you can also measure the speed, and when you plot those against each other, what you find is that these distant galaxies, the ones right in the far reaches of the universe, are all moving away. And actually all the others are moving away from all of the others as well. But the ones the furthest out seem to be moving the fastest. And then you can question students and get them really thinking. So, okay, if all of the galaxies seem to be moving away from one another, let's imagine you were to play the video of the development of the universe backwards. What would you expect to happen? Well, then you can draw another diagram like this, showing what you would expect to happen. And actually what you would see is, if we draw the Milky Way here, what you would see is all of those galaxies much closer together. So this is the universe now. So if we have rewound the tape, then the universe is much smaller. Now if you carry on this, and for reasons of space I'm going to have to go this way, but if you were to carry on this, well, what that implies is that at some point all of those galaxies, I'm going to shade this to show that this is really kind of dense and concentrated now, all of those galaxies were in one single point. All of the matter, these billions and billions of stars, planets, galaxies, whatever, all of those were in one tiny point. And the idea is that something must have happened here that caused everything to then start exploding outwards. And this time at which they were all together, we call the Big Bang. There must have been some explosion that set those off so that we get to the picture where we are now. And the final thing you might want to do, again, this is not essential, but I think it's interesting. Scientists, based on the distances that the stars have travelled, scientists have estimated the age of the universe. How many years ago was it? How far would you have to rewind the tape to get to the Big Bang. And it's about, off the top of my head, 13.8 billion years. That estimate changes, so I would have to look it up, whether that's changed or not. You can look that up, or ask your students to look that up. But the point is, this gives us an estimate of the age of the whole universe. But then there's all sorts of questions. Okay, let's go back 14 billion years. What was there? And these are questions that we don't have the answer to. There's lots and lots of stuff that we don't know about the universe. I haven't even gotten to dark matter. So the fact that the universe seems to be accelerating, so the fact that these ones on the outer reach of the universe seem to be moving faster, well, that's because of dark matter and dark energy, and we don't really have a model to explain why that happens. And what I would emphasize here, and this is a really nice opportunity to emphasize this, is that science can't give us answers about everything. At the moment, we're still trying to work out what happened before the universe. There's this theory, people call it the Big Crunch, that there was this kind of supermassive black hole which brought everything in together, and everything kind of collapsed into one place and then exploded back outwards like this. But we don't know, and we have to continue with our model of making guesses and then doing our deductions and checking with any experiments that we can do in order to find new knowledge. So this is a really, really exciting lesson. I think the main thing to emphasize is this idea of scale. There's also, the last thing I need to remember, there's also one extension question about kind of the relationship between science and religion. And again, students will have, I'm sure students will have questions, well, didn't God create the universe, and so on. And again, this is a really good opportunity to talk about that relationship in a nuanced way. So rather than saying religion is just wrong, we can say, well, science, we have this process that generates evidence, but there are some questions that science can't answer. And what came before the universe? Well, that's one to leave open. In the next lesson, we will start on forces. Thank you.